We have seen how electricians and electronic engineers have created short-form diagrams to represent a lot of information into a small and yet easy to follow notation. This makes it easy to understand and replicate. However, these diagrams do not solve the logic they represent. Moreover, there may be ways of reducing the number of components required by analyzing the logic via truth tables and outcomes. This analysis and its associated mathematics is called Boolean algebra. After completing this lesson, you will be able to match and identify Boolean statements and the logic they represent, convert a logic gate diagram into a Boolean mathematical statement, and explain the four principal laws regarding Boolean algebra and how they apply. In the last lesson, we discovered how logic gates can represent simple electrical circuits and problems. To review, in order for the output C to be on, both the A switch and the B switch must be closed. In electronic logic, when inputs A and B are both true, then C will be true. But can we convert this into a simple mathematical statement? This logic says that A and B must work positively together to generate an output. They are inseparable. That is, the circuit does not work without them both being on. So let's stick them together and use an equal sign to see what happens to output C. We get AB equals C. Congratulations! You have just written your first Boolean logic algebraic expression. Although we don't call it multiplication in Boolean, we use that symbology to represent the AND logic function. And the AND function can also be expressed as A times B or A brackets B. Boolean algebra was conceived by George Boole, who was a self-taught 19th century English mathematician. He devised a method of logical analysis. Initially, he was looking for a simple method to express quantitative statements in algebraic form. He proposed that A times B should represent the AND proposition, and the A plus B should represent the OR proposition. Boolean algebra has been expanded and is used to solve logic gate problems. It is fundamental in developing electronic circuits. In many modern diagrams, the output has been reassigned to the letter Y. This avoids confusion with multiple input devices. Just like our logic gates, there is at its core, however, two simple statements: the AND statement and the OR statement. This may appear confusing at first, since in arithmetic, plus means add together. But it does make sense when you examine it from a commutative operation perspective. In math, A plus B is the same as B plus A. Furthermore, A times B is the same as B times A. Here, the outcome will be the same regardless of the order of the numerical components involved. However, whereas this reversal of numerical component order does not matter in addition or multiplication, it does not work in subtraction or division. A minus B is not the same as B minus A, and A divided by B is not the same as B divided by A. Logic is about operational outcomes rather than mechanical operation. As we've seen before, the actual input devices and output devices are irrelevant. It's only the desired interaction of those devices we are concerned with. When we create logic, we cannot have any ambiguity or confusion. Shoving A and B together as an AB shows there is only one interpretation. They must be together to achieve the desired outcome. It has only a singular possible outcome. Since there can only be one possible resolution, the exact order of the inputs does not matter and can be expressed as BA without confusion. By putting a plus sign between the inputs, A, B, shows that there are additional possible outcomes. Okay, let's apply this to some of our logic gates. The AND gate gives us AB equals Y, which functions the same as BA equals Y. We could also say that A times B equals Y, which functions the same as B times A equals Y. The OR gate gives us A plus B equals Y, which is the same as B plus A equals Y. And the plus sign here, of course, means OR. So A or B equals Y, which functions the same as B or A equals Y. Okay, so Boolean works on simple gates. But what about more complicated circuits? Well, it's just like math. Here's a combination of AND gates and an OR gate. Below is the relay logic if you wish to follow along. In order for Y to be true, the A and B inputs of gate 1 must be true, or the A and B inputs of gate 2 must be true. Okay, so we can express larger, more complicated circuits using basic mathematical rules. Great. However, we have not determined how to show not true results or not true inputs. Let's say we want to start a motor. We know that we have to be in automatic, but at the same time, we want to make sure it is not in manual and there hasn't been an e-stop button pressed. How do we show that in Boolean? How do we indicate something is false? Well, looking at our relay logic, we're going to steal something. Notice that the manual has a line through it. We're going to use a line in Boolean. The not condition, whether on an input or on an output, is represented with a line above the input or output. Looking at our table, we have not A, not B, and not Y. When we look at the next line, we have A and B together with a line over top. This is not AND AB or NAND AB. There's different ways to express it. The one below that, we have the bar across the A or B. So this is nor A or B, or neither A or B. On the bottom, notice we have the line over one element, but not the other. So we have not A and B. And the second statement is A or not B. If we look at the gates we have drawn, the bottom has a little dot on one of the inputs. This is the same as saying that it's been inverted. Here's a table with our familiar logic gates and converting it to Boolean. We have our AND gate, A and B equals Y. Then we have our NAND gate. A and B is equal to not Y. We have our OR gate, A or B equals Y. And then we have our NOR gate, A or B equals not Y. Here we have two gates with their inputs inverted. You would think that the output would be the same, but we express it a little bit differently. On our new NAND gate, it's A and B not equals Y. And on our new NOR gate, A or B not equals Y. Notice we don't split the lines. This is going to be shown very clearly that by splitting the line, a major change takes place. Let's take a look at some other rules regarding both algebra and Boolean algebra. The commutative law of addition or multiplication remains the same. This law simply states that if the same operator in mathematics, addition or multiplication, is used, the order of the elements A or B does not matter. A or B is the same as B or A. In math and in Boolean, we have the associated law of addition. For example, if we have A and we add it to B plus C, then that would be the same as saying A plus B plus C. In Boolean algebra, the ORing of any number of variables will ultimately achieve the same result. You can then simply group them as you require. In our example, we have A or B, or C or D, or E. Any one of those would satisfy and turn on our Y. The associated law of multiplication simply states that when several variables are ANDed in groups, the order makes no difference to the outcome. A and B, C and D, and E all must be true to turn on Y. The distributive law, A and B or C equals AB plus AC. This equation means that ORing several variables and ANDing the result with a single variable is the same as ANDing the single variable to each of the other variables and then ANDing the result. This distributive law equation is only true in Boolean algebra. It states that when a single variable is ORed with a group of ANDed variables, it's exactly the same as ORing the single variable with each of the grouped variables separately and then ANDing the result.
Logic, the vast majority of the rules apply, but be careful when evaluating not logic. For example, A and B not equals Y is essentially the same as A naught and B naught equals Y. These two statements appear to be doing the same thing. Same as A or B naught equals Y, or A naught or B naught equals Y. However, they actually mean different things. Something happens when the line is broken. Looking at A and B naught equals Y logic gate, the inverters are before the decision point. That is, the inputs are inverted. Whereas A and B equals Y naught, it means the outcome is inverted. With the Boolean expression A or B equals Y naught, the output is inverted, whereas A naught or B naught, the inputs are inverted. Clearly, the order of operation counts. Something odd has happened here in the seemingly simple transformation. Looking at the two truth tables of A or B naught and A naught and B naught, their outputs are the same. And the A and B naught and the A naught or B naught truth tables, their outputs are the same. British mathematician Augustus de Morgan noticed this, and he summarized it this way. Not A or B is equal to not A and not B. Furthermore, not A and B is equal to not A or not B. Actually, that's not quite what he said. What he said was, the complement of a union of two sets is the same as the intersection of their complements, and the complements of the intersection of two sets is the same as the union of their complement, which is really confusing. Basically, it's come to be known as this. You break the line above, then change the sign below, or, even simpler, break the line, change the sign. This law is easy to remember. If you break the line, change the sign. Algebra is a mathematical representation of logic. Its biggest strength is the ability to reduce complicated logic into a simple equation. The simplification process can reduce the number of logic gates and therefore the number of components needed.